Hey AP Chemsters, this is Mrs. Vanderwall bringing you another edition of the Blank Wall series. So today we're talking about 16.3 buffering effectiveness, the buffer range, and the buffer capacity. First of all, let me remind you that if you should have a calculator with you, you should have your notes, you should pause this when you need to. Please, please, please follow the calculations along with me so that you are getting used to the procedures of how to solve these problems. All right, so let's start off with what factors influence the effectiveness of a buffer. If you recall what a buffer is a system that will resist change in pH. And I know the problems that we did in section 16.2 hopefully proved to you that if you put an acid, a strong acid or a strong base into just regular water, the pH is going to go crazy. But if you put it in a buffered solution, it's not going to change all that much. Some of the problems that we did showed you that the percentization will change, but not drastically. And so is there a limit to how much a buffer can hold? Is there a limit to how much of this acid and base you can add to the system before the buffer can no longer resist changes in pH? And you might have already guessed the answer is yes. So this section is dealing with, okay, well, what kind of things will we be looking at to know how effective this buffer is? And one of the things we're going to be looking at is the relative amount of the acid and the conjugate base, meaning what is the ratio of their molarities. The other thing that we need to look at is what's called the absolute concentration. What is the actual molarities? Is there a better system than others? Will a high concentration be better than a weak concentration or a low concentration? So those are the things we're looking at in this section. So let's look at the first one, the relative, the ratio, in a sense, the amounts of the acid and the base. So it says the most effective buffers, which are the most resistant to changes in pH, are when the concentrations of the acid and the conjugate base are equal. So if we have the same molarity of the acid and its conjugate base. So for example, assume a buffer with this hypothetical HA and a negative with a pKa of 5.0. So we're going to make that buffer setup. So in case number one, we're going to use the same moles. Now wait a minute, I thought up above we're talking about molarity, and now you're just giving me moles. Where's the volume? Well, I don't know if you've caught on to this yet, but as long as they're in the same beaker, they have the same volume. So if they have the same volume, then the ratio of the moles will be the same as the ratio of the molarities. So we can get by without knowing what the actual volume is as long as we're only concerned about their ratios, which in this case we are. So let's check this out. I have 0.1 mole of this weak acid and 0.1 mole of its conjugate base, and I'm going to add 0.010 moles of a strong base sodium hydroxide. So let's find the initial pH, the final pH, and the percent change. Okie doke. So the first step, the initial, I'm not adding anything. So this is pure equilibrium right here. And if I'm just talking about equilibrium, then I am free to use the Henderson-Hasselbalch equation, or otherwise known for me as the HH equation. So this is where pH is equal to pKa plus the log of the base of the acid. Well, fortunately, they gave us the pKa is 5.0. Okay, now let's do the log of the concentration of the base. This is log. Of the base of the acid, which is 0.10 over 0.10. Well, what do you notice about the ratio of the moles is the same as the ratio of the molarity? I just told you that. The ratio is equal to 1. Well, what's the log of 1? Go ahead and plug that in your calculators. What's the log of 1? Did you see that's equal to 0? So in this case, pH is equal to pKa, so the pH is equal to 5.0. So now what? I'm going to add some base. So this is where my stoichiometry comes in. Okay, so I'm going to have a BCA table. Let me erase part of this. And so for the before I do anything, I know I have this much of my acid and this much of my base. And again, my units are moles. And so now what I'm going to add some sodium hydroxide to the system. And I had already set it up where I am showing you that the hydroxide is going to react with the weak acid. All right, hydroxide's not going to react with a base, it's going to react with an acid. So that's why I put it with the HA. And so now what? We're going to have a change set up. Well, I'm going to use up all of my hydroxide because it's in the lower amount. And it's going to react with some of my acid. And I'm going to gain some more of my base. Okay, so when I'm all said and done, these guys cancel out. I end up with 0.090 moles. And I have 0.011 moles of my conjugate base. All right, so now I'm ready to do my equilibrium again. So I'm free to use my Henderson-Hasselbalch equation, and I'll plug in these values. Log of my base. My base is 0.100. This is my base right here. Oops, wrong one. Let me try that again. And I'm going to this right here. That's my base. Over my acid. There's my acid right here. So go ahead and pause this. That says 0.090, by the way. Pause this and see what you end up with. All right, I sure hope you got the pH of 5.09. So if I added 0.010 moles of sodium hydroxide, the pH only went up by 5.09. And does that make sense? Yeah, the pH went up. It's your base. So 5.9 is slightly more basic than the initial setup. Now, a percent change, by the way, percent change is a final minus initial over initial times 100%. So what was my final pH? That was your 5.09 minus 5.00 over 5.00. Don't forget to multiply it by 100%. Go ahead and do that. What do you get? Okay, hopefully you did your work. And I got 1.8%. So that's my final change. Okay, not too much different from the initial pH of 5. So let's try the next setup. Look at what's different. I have a big variety or big change in the amount of my weak acid and my conjugate base. So let's go ahead again and do the same setup. Why don't you pause this and do the entire procedure like what I did in case number 1. Go ahead and do that on your own. Pause this and work it out. All right, how did you do to find the initial pH? Did you get an initial pH of 4.05? Notice, because you have much more of this weak acid than you do of your conjugate base, that the pH dropped to acidic level. All right, if you haven't done so, let's go ahead and do your stoichiometry. I'm going to have to erase some of the first part. So if you did your stoichiometry, notice here are the numbers that you have. You start off with 0.18 moles of HA and 0.020 moles of the A negative. You add 0.01 moles of your base. It's going to react with your acid. So you're going to end up with 0.017. This is 7 moles of the weak acid and 0.030 moles of the A negative. Okay, use those numbers now and plug into your final equilibrium. Go ahead and do that. So now I have a final pH of 4.25, and now we need to find the percent change, which I'll just do it right now. So it's your final 4.25 minus initial 4.05 over your initial times 100%. And if you'd like to do your math, make sure that I'm doing it right. Why don't you do that right now? And I got the percent change of 5.0%. So compare case 1 with case 2. Okay, so case 1, we only had a 1.8%, and in case 2, I had a 5% change. So yes, the relative concentrations do make a difference. So our conclusion is in order, and this isn't a very important conclusion, by the way, so why don't we do like star this one, all right, do something to make sure you are aware of this. In order for a buffer to be reasonably effective, the relative concentrations of the acid and conjugate base should not differ by more than a factor of 10. All right, the factor here was a 0.18 and 0.020, so the factor is close to being a 1 to 10 ratio, but not quite. and the percent change was 5%. If you change it much more than that, it's going to get much, much, much worse. So this factor of 10 is a big deal. So let's go over here. Let's talk about this idea of absolute concentration. So we're talking about the difference between a low concentration versus a high concentration, okay? So what does it say here? A buffer is most effective when the concentration of the acid and the conjugate base are high versus low. So let's look at the exact same buffer with the exact same pKa, and let's see what's going on when we have a high concentration. This is your case number 1. Maybe you want to write this down, that this is a high concentration, and let's see what's going on here. So very, very same setup. I bet you could do the first part all by yourself. You probably don't need me. Notice that these have the same values. So we're looking at, again, 5.0 plus log of 0.5 over 0.5. Hey, that's 1. And the log of 1 is 0. So the pH is equal to 5.0. And now look what happens. Okay, erase some of this. So here we have 0.50 moles and 0.50 moles. This is my before. I'm doing my stoich, right? And so I'm going to now add that many more moles again, and I'm going to use them all up because it's in the lower quantity. So what do I have here? This is 0. This is 0.49, and my conjugate base is 0.51. So look at, their ratios are still almost the same. So let's do this again, is equal to 5.0 plus the log of my base. Here's my base, 0.51 over the log of, or my acid, which is 0.49. Go ahead, pause this, and go ahead and do the math. I don't know about you, but the log of 0.51 divided by 0.49, that's 0.51 divided by 0.49 is 1.04. The log of that is barely a positive, or 0.017. I rounded up, so it's 5.02. So now what? Well, we got to find the percent change here. Let me erase this. All right, and so the percent change, just like what we said before. So percent change is final minus initial over initial. 5.02 minus 5.00 divided by 5.00. Well, you go ahead and do the math, and you're going to see it's a very, very small percent, and it's 0.4%. Okay, now will you go ahead and do case 2 all by yourself? Go ahead and pause this and do the whole thing by yourself. So here we go. Equilibrium, again, the ratios are the same. So your pH is 5.0. Here's my stoichiometry where I have a 0.5 and 0.05, 0.05. Stoichiometry out of 0.04 moles and 0.06 moles. So when I actually do the equilibrium again, remember that even though these are moles, we're talking about the ratio of moles is the same as the ratio of the molarities. So this ratio here, the log of that's 0.176, I guess. So this should be 5.18. And you get a 3.6%. So once again, the lower the concentration you have, the higher percent change. So it says the buffer with the greater amounts, the higher concentrations of the acid and conjugate base are going to be more resistant to pH changes and more effective buffer. Let's turn the page. So this is a buffer range. Now I think Jonathan is getting all excited because he's seeing the word range, and he's thinking he's going to go back and feed on some grasslands on the range or something. No, Jonathan, that's not going to be your dinner. Go away again. All right. Oops, he's back. I think he went home on the range there. So we're talking about a buffer range here. So what is the range in which you're going to have a good buffer? So it says go back to the relative amounts. Remember how I told you back a couple pages ago? Let's go back here. Look down at the bottom. Remember I even told you to star this because this is really important. It says that the relative concentrations of the acid and conjugate base should not differ by more than a factor of 10. That's a big deal. All right, go back to their page 10, I guess. So it says they're no more than a factor of 10 different. So use the Henderson-Hasselbalch equation to determine the buffer range. All right, so let's see here. pH is equal to pK plus log of the base over acid. So let's just say this, that the base is 10 times bigger. If that's 10 times bigger, that's really as maximum as you can get. Well, what's the log of 10? Isn't that equal to 1? So we're saying take the pKa and just add 1. So that's your upper limit of your buffer. Well, what about over here? What if your acid is actually 10 times as strong as your base? So now this is a log of 0.1. And what is a log of 0.1? It is -1. So the pKa is a lower range, pH is pKa -1. So my range is really plus or minus 1. So going back to that previous problem where we had the pKa is 5, that buffer, in order to prepare it, should have a range of either 4 to 6. Okay, so add 1, subtract 1 from your pKa. All right, so it says which acid, hang on, there we go. Which acid, whoops, should you choose to combine with sodium salt to make a solution buffered at a pH of 4.25? For the best choice, calculate the ratio of the conjugate base to its acid to attain the desired pH. So it's not enough just to know, all right, I need a plus or minus 1. I need to know what this ratio right here is. That's what they're asking me to find. All right, so first of all, find your pKa, and you want 4.25 to be within plus or minus of these numbers. So that's going to be a little bit too low. That's a little iffy, isn't it? So if I take 4.25, that's going to be close. If I added 1, that's going to be kind of close to this one. Is there a better choice? What about formic acid? What if I were to add 1 to 3.74? Do I get 4.74? That's within the range. Hypochlorous wouldn't be very good at all, because if I add 1 or subtract 1, it is not in this pH range at all. So I'm going to choose formic acid. That's my choice here. So let's see what this ratio of my base to acid ought to be to get an exact solution of 4.25. So pH is 4.25. My pKa, they told me, was 3.74 plus the log of base over acid.